Hey kids, welcome back to Mr. Murray's Math Land, and we are continuing on with the disk method, and as you can tell by the title here, we're going to be doing some with respect to y here, and that means we're going to be going around a vertical axis. We're going to start with the y-axis though for the first example. Considering the region in the first quadrant that is bound by the y-axis, the graph y equals e to the x, that nice exponential growth there, and the horizontal line y equals 10. So here's your region here, y-axis, exponential curve e to the x, and horizontal line y equals 10. There's your region. And what am I revolving it around? If I were revolving it around the line y equals 10, that would be a disk method. It would, it's right up against that axis of revolution, and I would be doing it with respect to x. I'd be doing dx. But they're asking us to revolve it around the y-axis, and that axis of revolution is always important. It kind of dictates how you approach the problem. If you're going around the y-axis, or any vertical axis, as it will be, it means you're going to be integrating with respect to y, and that means you need your equations to be in terms of y. So this right in particular here, this y equals e to the x. We want to solve that for x and have it in terms of y, but that's an easy fix. That's ln of y equals x, right? If you just take the ln of each side there, ln of e to the x is x. So this graph right here can be called x equals ln of y. Okay, now what are we revolving around? We are going around this y-axis. So if you like a little visualization here, this piece will be going around in this direction here, and that means you're going to end up with, another one of those kind of bell-shape figures, but right here, and your circular cross sections are going to be looking like that, right? As you get towards the tip of that bell, the circles get smaller, and your radius, which is the important part, is that distance from the outer edge of the region to that center, that axis you're revolving around, or in this case the y-axis. So there's your radius in each case. And one thing that's important that tells you you're using the disk method as opposed to one you'll be learning in the future is that when you're revolving it around this axis, the region you have here is right up against the very axis you're revolving around. There is no space between the region and the axis of revolution. So by revolving it, you get a solid figure. There's, no holes in it or anything. You get a nice solid figure. And so we just got to describe the area of each one of these circles. Very easy. There's your radius. Your radius is always going to be the distance of your right boundary minus your left boundary, or in this case, that's just 0. And your right boundary would always be the x value on the curve at whatever point you're at, right? And the x value on the curve is ln of y. So r equals ln of y. And so our volume, same deal, just going to add up all the areas of those circles, pi integral from, now what are our boundaries? We are going with respect to y, which is why I didn't try to find the intersections, because I already have the y values of the region. It goes from 1 to 10. So 1 to 10 of pi r squared, and r is ln of y squared. With respect to y, definitely don't want to integrate this one by hand. So here we go. Pi, math 9, 1 to 10, new set of parentheses, ln of x is the only variable we use here. Close that, close the argument, close the set of parentheses there, squared, with respect to x. And we get about 78.437. 78.437. So not really much harder. than doing it with respect to x. Just there's occasionally that little trickery, and you're not as used to doing things with respect to y in general in math. So it's that can make it a little trickier, but basically the same premise. And so of course the disk method, the formula is the same. It's pi r squared, right? Area of a circle. You're just doing it with respect to y whenever you're going around a vertical axis. And so maybe I'll just make that obvious here. You're using dy when you go around any vertical axis. And that means when you're going perpendicular to a vertical axis, that means your radius is horizontal. So sometimes it's a little tricky to keep that straight. And your radius is always right minus left. Just like your vertical radius is top minus bottom, you always take the bigger minus the smaller. So right minus left. Okay. So let's just see another example. Consider this region, f of x equals root 10 minus x plus 2. That's the square root graph. That negative is reflecting it that way. It's shifted 10 units to the right and 2 units up. Nicely given to us by the graph. You're welcome. The y equals 2, x equals 1. So we're talking about that region. All the intersection points have been given to us. How nice. And now we're going to revolve it around x equals 1. X equals 1. Now when these are all mixed up, you got to ask yourself, are we doing this dx or dy? We're going around x equals 1, which is vertical. So that means you're doing dy, right? This is just like another version of the y-axis, just shifted. So that means I need my equation here in terms of y. So this is right now y equals root 10 minus x plus 2. So solve this for x. Subtract 2 from each side. Square both sides. Subtract 10, divide by negative 1, or move the x to this side, move the quantity to this side, however you like to do it. X will be 10 minus the quantity y minus 2 squared. If you want to FOIL that out, be my guest. But that is the equation here. X equals 10 minus y minus 2 squared. Okay, so now we're revolving it around this axis right here. And again, it's a disk method because the region is right up against the axis. There's no space between the region and the axis. And when I revolve it in this direction, you're going to get kind of like this flattened Hershey's Kiss kind of shape. And so your circles are going to be looking like this, right? Big circle there at the bottom of the Hershey's Kiss. And your radius of each one of these is going to be the distance between the curve and the axis. You're going horizontally, so you want your right boundary minus your left boundary. Okay, so our radius, wherever we draw it, our radius is going to be the right, which is 10 minus y minus 2 squared, minus the left, and the left is not the y-axis, the left is 1, x equals 1. So that's that, and you can simplify that a little bit if you like. 9 minus y minus 2 squared, and that is the radius of each one of those circles. And if you can do that, then you're practically there. That's the toughest part, I think, is setting it up, visualizing it, correctly describing that radius. The rest is just plugging it into a formula. And so the volume is going to be pi times the integral from what are our boundaries. We're doing it with respect to y. So think this here along the y-axis. What are our boundaries? From 2 to 5. From 2 to 5. 2 to 5. So focus on y values when you're doing it in terms of y. So pi times the integral from 2 to 5 of the radius squared. That's a big quantity. I'm just using brackets to make it stand out a little bit more, but you could use just another big set of parentheses, of course. Squared dy. Don't forget that differential. And let's go get it now. Okay, so pi math 9 from 2 to 5. New set of parentheses, 9 minus new set of parentheses, x minus 2. Close that quantity, square the x minus 2, close the entire radius, square that entire radius, dx. Okay, and you get about 407.150. 407.150. Okay. Very cool. So now, just so you see the difference here, what if I take the same shape, same region, same boundaries, but I revolve it around the line y equals 2, which is the bottom boundary of the region. So if I revolve it around here, this is a horizontal line. That means we're going to be doing this with respect to x, right? This is like the x-axis, so just moved around. And so it means I want to keep it in terms of x. So this right here was f of x equals root 10 minus x plus 2. And if you like that visualization, we're revolving it in this direction. So again, you get more of a, a bell shape again. So this one you get sort of a short but wide one. This one you get sort of a longer kind of shape. Since it's the same region, do you think it's really the same volume? It doesn't really matter how you rotate it? Oh, let's find out. Maybe you can think about it before we get there. But the radius, what you want to describe, is from there to there, right? There's the center of the region. There's the axis you're revolving around. Again, it's going to be a disk method because we're right up against, the region is right up against the axis of revolution. So your radius is right there. Your radius is always going to be the distance from this curve to this horizontal line, or the difference between them. So our radius is top minus bottom. The top boundary is root 10 minus x plus 2, or you could just call it f of x if you like, minus this horizontal line, which is 2. That kind of works out nicely. It takes away that 2. So that's just root 10 minus x. And now our volume, pi integral, what are the x values of the region? We're going from 1 to 10, pi r squared. So, I'm writing this out. It's root 10 minus x squared, but of course, that's just going to leave you with 10 minus x. So that's what I'm going to type in the calculator. Kind of nice. And here we go. Pi math 9, 1 to 10, 10 minus x, right? Because I squared that square root. So that's gone with respect to x. And there's our answer. Notice it's a lot smaller. It's a lot smaller because even though it's longer in this direction, those circles are so small. Whereas here, those circles are really so big. That's a lot of volume. If you really were going 3D, that'd be like coming out at you. That's a lot of volume. Whereas here, it's kind of tight, so you can think about a short, wide cylinder versus a long, skinny one. The short, wide one is going to hold more stuff. So that was about 127.235. 127.235. And there we go. Another day in the books, kids. Hope you're loving the disc method. And if you're still watching and you've paid attention this far, feel free to leave a comment for a bonus point about, who's your favorite musical artist? All right. Have a good one, kids.